It's a pleasure to be here with you in this IEEE LATINCOM conference. My presentation is about the M-QAM modulation technique effect for an OFDM-RoF-XGS-PON converged network. I am the speaker, Andrés Felipe Escayón, and this work has been, I have been supervising this work with other co-authors, Christian and Edward. We belong to the Electronics and Telecommunications Engineering faculty from Universidad del Cauca, Colombia, and we belong to the research group in New Technologies in Telecommunications, GNTT. Okay, let's start. This paper focuses on analyzing at the simulation level the effect of the MRE quadrature amplitude modulation technique for an orthogonal frequency division multiplexing radio over frequency converged network infrastructure based on the XGS-PON standard. The above with the purpose of determining the network performance as both the order of the M-QAM modulation and the distance of the optical link are increased. So we have the context, the contents of these presentations, where we'll cover the context, the research, theoretical framework, result analysis, and at the end, conclusions and future works. Okay, talking about the context, the proliferation of mobile and other wireless devices, along with the growth and development of broadband services and applications, creates pressure on the wireless access networks to increase its capacity. So as you can see here in table 1, we have outlined the optical and wireless networking characteristics, so the fiber optic systems versus the wireless systems. So we have electrical noise immunity, such the characteristics for the fiber optic systems are electric noise immunity, signal security, high bandwidth, high capacity of data transmission, low attenuation and long distances, and the protection of the environment. And the wireless systems have these characteristics, mobile, or these features, important features, mobility of users, low cost of installation and maintenance, constant connectivity, direct access to many new services and applications, and the use of digital modulation and multiplexing techniques, and the convergence with other networks. It is important to drive the convergence between wireless and optical technologies to the last mile, defined as fiber to the home and radio over fiber architectures to provide high capacity and high speed data transmission in access networks. So in figure 1, we can see the next generation heterogeneous broadband access networks based on radio over frequency, radio over fiber, with the central office and the cells in the base stations and all the connectivity that we can see over there. In the figure number 2, you can see the evolution of passive optical networks through the years, from starting before the year 2000 with BPON, going along until the year 2005 with GPON and EPON standards, then getting the year 2010, we have the 10G EPON and XG-PON, and recently the standard NG-PON2, the XGS-PON, which this paper is based on, is a kind of coexistence or overlaid model of OFDM over this XGS-PON infrastructure, and then we can encounter the other ones like the NG-EPON, NG-EPON, and the GHESP.X for higher speed PON passive optical networks. And we have outlined this here, the two standards. One in purple color is the I2T Q2 SG15, and the orange one is the IEEE 802.3. And you can see on the y-axis the difference in the downstream and upstream data rate in bits per second for each of the standards. And so we have to focus our attention on the XGS-PON 10 giga, which is symmetrical, 10 gigas for the gigabits per second for the downlink, gigabits per second for the downlink, and 10 gigabits per second for the uplink. But we have our test or simulation scenarios that consider this infrastructure, but only considering the downlink because of, or due to some restrictions in the simulation software, in the OPSIM simulation software. Okay. So in figure number 3, to finish about the context, we have the FTTX architectures for XGS-PON scenarios. So you can see on the left the different FTTX architectures, and then how these are connected and distributed in order to deploy a XG-PON infrastructure, as you can see there. Then the research problem that we covered, or that we were working on, was the convergence of wireless and optical networks in a technology such as radio over fiber. ROF is currently the subject of constant research. This paper focuses on what is the M-QAM modulation technique effect for an OFDM ROF over XGS-PON converged network, which I thought this is a kind of overlaid model. So it's important to talk about the theoretical framework, to recall something about the M-QAM. It defines that the information signal is contained in both the amplitude and the phase of the carrier signal. We have this equation that let us work on this topic. The technique transmits two independent messages from the same carrier signal, where the messages occupy the same frequency band, but are offset 90 degrees from each other. The other one that we have to consider is the OFDM. Also, we have an equation that describes it. And in the figure 4, you can see the OFDM signal in the frequency domains with the corresponding orthogonal subcarriers. And to finish, the radio over fiber architecture is a combination of wireless networks with fiber optic networks, where the radio frequency signals are distributed from a central office through a fiber optic link to a base station. As you can see in figure 5, the general ROF architecture is displayed. So you see how the signal is the RF signal receiver gets that information, and then goes through a baseband modulator, then continues with using an optical source, the RF to optical up converter, and then we have the optical link, and from the transmitter to the receiver is doing the complementary operation with the optical detector and optical demodulator, and to finish with the demodulator in the electrical domain to the system terminal. The error vector, in talking about the OPM, the optical performance monitoring, we need to consider this because the error vector magnitude, EVM, measured in the receiver seeks to evaluate the quality of a certain signal that has been modulated with some multi-level modulation technique, such as M-QAM or PSK. So in figure 6, you see the graphical representation of the EVM, where you have the I and the Q, the in-phase and quadrature axis. So you see how, if you have a reference and if you have the measure one, so you can compare and you can get the AVM, which is like the difference in the positions from the reference in the transmitter to the obtain point in the receiver. So you have the error vector magnitude over there that is going to be useful for us to compute or to calculate the error, and thus see the performance of this simulation that we're gonna work on. It is possible to obtain the BER as a function of the signal-to-noise ratio for a network module using the M-QAM modulation technique, as outlined here in this equation of the BER as a function of M, which is the MRE that we have been talking about. It is also possible to obtain a consistent approach to the signal-to-noise rate as a function of the EVM, which is the other one showing the SNR in decibels as a function of EVM. Okay, so we can get this information, which are some important OPM parameters that will help us decide or analyze the performance of this proposed research. In the table 2, we have the characteristics of the simulation scenario that we used. So the parameter and the value. The data rate used was 10 gigabit per second. The RF radio frequency carrier frequency, RF carrier frequency was 10 gigahertz. Modulation formats used 4 QAM, 8 QAM, 16 QAM, and 64 QAM. QAM. Okay. The inverse fast Fourier of the subcarriers were 8. We used 8 subcarriers. For the OFDM, yeah, the cyclic preface was 0.25 gigahertz. I am not sure that, I think it's only 0.25. Okay, delay 0. The band was the band C. We used signal wavelength 15 nanometers. Where the RF video is. The continuous wave laser frequency was 193.4 terahertz continuous wave. Continuous wave laser power 0 dBms, laser wavelength 1550 nanometers. Optical modulator used was a Mach Zehnder modulator, optic fiber I2TG, the standard one. Okay. Photodetector used was the PIN. Photodetector wavelength 15 nanometers. And electric filter receiver 1 and 2 was a bezel filter with 7 number of poles, and the optical filter was a root raised cosine filter roll of a half 0.5. Okay, so in order to conclude this, is where we're heading now to the results analysis. You see there the simulation scenario is we used OFDM, which is a software that allows us to work with optical radio and optical convergence. So you see on the top left the OFDM-RoF radio over frequency module. Then we have like the reference. The first on the top you have like the back-to-back simulation scenario, or the back-to-back scenario as a reference. But you can connect the transmitter with the receiver using the infrastructure with the fiber, and based on the XGS-PON standard, okay, but contain only the downlink, and overlaying FDM with this infrastructure of XGS-PON. Then you can see that for the overlay, the results here for the overlaid OFDM-RoF over XGS-PON system with 4 QAM modulation scheme, a maximum distance of around 3.2 kilometers was achieved from the transmitter to the receiver in order to have like a good performance, or the minimum acceptable performance. You see in the figure 8 graphic results for the OFDM-RoF over XGS-PON system for 4 QAM, and you see some results over there. The signals in the frequency domain, and also at the end the constellation for the 4AM and the high diagram. Okay, showing good results, good performance over there. Then continue, because we of course varied from 4 to 64 QAM. For the overlay model, a system with a QAM modulation scheme, a maximum distance of 5 kilometers was achieved. So we see that we had a better coverage. We increased the distance in almost the double, 5 kilometers. You see the results of this scenario, and also in the multi-level format for the eye diagram and the constellation. Okay, in comparison with the reference, which is in blue, obtaining a good performance, the minimum acceptable. And then we move to 16 QAM, okay, where the distance was also increased by a little, but representative, 5.6 kilometer, and you see the results over there. Okay, so continue doing so with the 64 QAM and the information obtained in got from the simulation tool. We see that we finally got better or more distance, which was 6 kilometers, increasing the M-QAM. So at the end, we have to analyze like the behavior for the effect that the M parameter has with the QAM format modulation, in order to compare and to see the effect. So according to the analyzed data from the M-QAM modulation scheme for the overlay OFDM-RoF-XGS-PON system, converging network infrastructure, we have these results. Figure 12, as we have the signal to noise ratio versus distance for M-QAM. So you see how varying from 4 to 64, how the distance is outlining in the x-axis, and the SNR is in the y-axis, showing how this is going to normally decreasing as a function of the distance, but also the effect that has that if you increase the M in the M-QAM, you tend to have a better performance. Yes, but it's important to consider the other results. For example, here in the figure 13, SNR versus distance for M-QAM, according to the analyzed data, we can see that if we compare, the other one was the same, but with SNR. Now, if we compare with the BER, we see the behavior, and we see that I would say 16 QAM is like the one that is having the best performance. Okay, in terms of OPM, could be 8, 16. Okay, so here is before the conclusion. We have a summary chart, a summary table with the characteristics of the simulation scenario. We see all the parameters that we are like remarking here: maximum distance, minimum SNR, maximum acceptable BER, transmission power, received electrical power, received optical power, and the receiver SNR. You can see that the 16 QAM is like the best. It is not only because of the distance; it's because you need to consider all the other parameters as a whole. So the conclusions are: an increase in the order of modulation leads to represent more bits per symbol and reach a greater distance without losing the transmitted information. The M-QAM multi-carrier modulation scheme can be implemented in OFDM-RoF converged networks together with XGS-PON access networks. The OFDM or RoF converged network model can be implemented on telecommunications networks to obtain multiple benefits. So as future works, it should be noted that the line of research can be extended as future work with the use of the XGS-PON standard for a two-way symmetrical link. So consider uplink and downlink. Thank you very much for your attention. You can reach us at these emails. It's been a pleasure to be with you, and I hope to see you in the next opportunity.